Okay, good afternoon, students. Welcome back to PCM 150X. Let me probably go to the start. We'll be starting on a new topic, and it's the motion in 2 dimensions. Obviously, it is a upgrade from motion in 1 dimension. So obviously, you have to grasp the concepts from there, which you'll need now um, for the 2 dimensions, which is obviously very important. So I'm assuming everyone is good with motion in 1 dimension, both in horizontal and vertical, for the free fall. And obviously, we'll be using those concepts and topic 1 as well. So it's one of my favorite sections because it actually includes both topic 1 and 2. And then obviously we are incorporating them all in all these problems. Okay, so motion in 2 dimensions. So it's not going to do all these questions. Right, so what I want to imagine, right? So let me rather explain it properly. I mean, it's a bit vague. So in 1 dimension motion, we talked about vectors, obviously, right? We're aware what a vector is. There's obviously things like velocity, acceleration. Obviously, with that, it has a magnitude and direction. But in case of a one dimension motion, for us to specify direction, it is quite easy, right? We either say it's up or down, where up would be positive and negative going down. Are we all content to that? Do we all understand that concept in 1 dimension? Just give me some thumbs up if you could do that. So in 1 dimension, I'll just repeat that again. We are dealing with vectors, but the only direction in that case was either left or right, up or down, being positive or negative. We're all happy with that, right? Okay. Thank you, Zizonke. Anyone else content to that? Thank you very much, Lebone. Thank you, Ms. Anthony. Okay. Now, when we're moving in 2 dimensions, we cannot simply use the up and down story. Things are a bit more complex. So, for two or 3 dimensions, we have to make use of the vector concept, right? And the vector concept is basically we're talking to the components. We remember components, the x and the y, and depending on the quadrant, things like that. The x component, the y component, cos and sine. Those things become more prevalent with dealing with 2 dimensions. Okay, so yeah. So in this particular thing, I want you to imagine an object, right? Starting at P, moving along a curved path from P to Q. I don't know if you guys can see that. Can you guys see that? I don't know if you can see my mouse pointer, right? Can you guys see that? And obviously, it's moving in space on an XY plane, right? That's obviously important. So I wanted to imagine P is moving, so put that in a moving image for you, running through Q. Okay, obviously, it's going through a particular time as well, which is obviously important. So what I have there is number one, the vector, the initial vector is Ri, right? Starts at Ri, right? And then eventually ends at Rf. Okay, so what we're representing there is just the first position on a curved plane. The reason why we're using it on this plane is obviously it's curved, it's not a straight line, so we need to represent it on an XY axis, and it's obviously moving in 2 dimensions, right? So we start on Ri and we're moving to Rf. What you notice there is the difference between the two, right? And that's why they have the delta R. And what you find out is that movement, or that change in movement, or the path traveled between P and Q is essentially the change in R. Another way of looking at it is basically saying, in a vectorial context, which is over here, we say R initial, right, which is Ri, plus the change in R will give us Rf. I hope you guys can see. We take Ri, we add change in R, and we get Rf. But as a vector, I want it to be clear, you're adding vectors over here. And in doing so, we're able to kind of, find where it is. However, what I want to make you aware of, in this case, for two-dimensional motion, obviously, we dealt with the first dimension, it was just x, y, or changing y, changing x. But in this case, we have to find the difference in the vectors. And remember, vectors, they have magnitude and direction. Is that clear to everyone? Did everyone get that? Okay, so I'm talking over here. So I'll say that again. From P, right, we represent that particular point at one vector at a particular time, Pi, and then we have Rf over there at Q. And what I'm saying is that for us to get Rf, or rather to change in R, we basically subtract the vectors Rf and Ri, and we find that there's a change in R, and that change in R is a displacement vector. And that is what I'm essentially saying over there, and which in this case is change in R for that line on top. So remember, always when representing a vector, there's always a line. What's important, going further from this, right, assuming that you've got me there, is that this, looking at the particular image, I'm taking the same image over here, which you have, right, this image over here, to P to Q, and just zooming it a bit now. So that's still P, and that is still Q. Can you guys see that? I'm just zooming it now, so you can see it further. Can you guys see that? Just bear with me, you'll get it, you'll get it. It's not that crazy. Can you guys see that path traveled? Again, I'll just go back. It's this one, that image at P to Q there, P to Q. And what I'm just doing, I'm not sure if you guys can see my mouse. I'm just zooming it up a bit. And then what you basically do now is that change in R, right? That difference in that displacement vectors has two components, the change in X and the change in Y. It is the change in X and the change in Y in one direction, as you know it. So you're essentially reverting back to the basics of the change in X and the change in Y. And I'll do a small example talking to this. And what we can do is represent that delta R into two components. It's obviously you're aware of this because it's a vector. It's the X component, and we can have the Y component. And what it essentially means, when it traveled from the first point P to the next point Q, it traveled a certain amount X, delta X, and a certain amount Y. Obviously, once we vectorially sum these two, the vector sum, we can get the actual vector, which represents that, but the actual path is just this, this curved path. So I'll say that again. We have delta R. We split it into two components. And what the components is saying for basically saying is that let's assume it is a total distance of 5 meters. We are saying change in X would move 3 in the horizontal and 2 in the vertical, and obviously downwards. And then obviously you vectorially sum it and you get that vector sum. But obviously the actual path is a path of curvature there. What's important to note is that we are basically we are splitting the vectors. But with that being said, let me revert to my blackboard and see if you guys got this concept. So yeah, that's basically it for now. You'll build on. You're gonna build on nicely. we will build on as time goes. You'll figure it out. It's not too difficult. Let me just quickly. So I'm recommend getting a textbook out in the meantime. While I'm doing this, just want to find that example. Let me find that example. Okay, it's a nice, cute example. And guys, we're reaching the end. It's nearly the 30th of May, which is going to be your mid-year test. Definitely will be completing the topic 4, at least most of topic 4. So make sure you're pulling up your socks accordingly. All right, so let me just quickly find that thing what I want to show you, or the example. Cool. So I'm just going to paste it and now let's talk about it. Okay. So this is a very basic example, right? And I want us to figure it out quickly. I want you guys to just. I'm gonna sketch the image for you now. Okay, before I think I don't want to sketch the image yet because I might give it away. Okay, I'll put it afterwards. Okay, it's a bit blurry, eh? So let me just get a more clear picture for you. I could have used a more better example, but okay, this is cool. Okay. So I want you guys to figure this out and see, and basically just we're doing the 2 directions thing. So I'm just going to share it now, and you guys can see. Okay. So I'll give you guys a few minutes, and then yeah. So just reading it off to you. We have a turtle, and I want to sketch it for you. Yeah, I know it's a turtle. It's quite strange. And this turtle is moving in this direction, right? To the horizontal at 25 degrees, right? It's moving at 0.26 meters per second. Just in case you want to know how fast the turtle actually moves. I'm assuming that's so what they're asking here. How far is the turtle move in the X and the Y direction, right? So it's moving from point, I'm just going to call it point O to point A, but they want to know in meters, right? How far does it actually travel in the X and the Y direction? So obviously we know, we can find out if we're smart enough how long it travel from here to here, but we don't know how is it on the X axis and how is it on the Y axis. You guys understand the question? You guys got it? So it's a very small example talking about motion in 2 dimensions. So I just want to try and articulate that. So let me just get a picture of the turtle for long. Then obviously I'll paste it. You can maybe see that turtle. Yeah, here's that turtle. Not sure it's worthwhile singing, but you get the idea, right? He starts over here and he's walking till there. And I want to know how far long has he moved on the X and how far he moves on the Y in meters. Is that clear to everyone? Using a concept of vectors or whatever. Does it make sense to everyone before I begin? Oh, just think of your vectors. Yes, sir. Okay, try it out and see. I'll give you guys 3 minutes, then I'll come in. I'll explain it obviously. Just a concept we to understand. We're not moving anymore. We're not moving this way. We're not moving straight anymore. We're not moving, left or right. We're not moving this way. Now we can move on a curve, and now we can move at an angle. So that's what I'm trying to articulate here. We're moving at an angle now. Okay, so just give it a go. Obviously, you need stuff of topic 1 Topic 2 didn't do so much vectors, but yeah, we need a bit of that stuff we did, that spice. Okay, so 20 past, I'll come in. Keep your answers around. Maybe I'll generate a poll. And we can. Nice. Other students, did you guys get it? Miss Bjerkes, I see you there. Melusi. I'm getting the same. Okay, fantastic. So let me just basically talk to this. Obviously, we have a bit of the concepts. The first way you want to maybe do it, you can say distance equals velocity times time. I hope you guys agree with me, or we can call it x if you'd like, or distance in this case, or we can this is this d I'm referring to, the velocity 0.26. We multiply that by 5, and obviously we should get an answer of 1.3 meters. So we know that it has essentially traveled 1.3 meters, right? In 5 seconds, 1.3 meters seems pretty decent. Makes sense, right? We think of a turtle moving after 5 seconds. It's like nearly the length of my leg. But we want to look at that in the x and the y direction. We want to obviously see what that looks like, and all we then have to do is split that into its individual components. X component, it will be d cos of theta. In this case, it's 1.3 cos of 25 degrees, right? And if you do that, you get an answer of 1.178, right? The smallest amount of decimals there, which is actually just round it off to maybe it's 1.18, right? Okay. Then for the y, okay, it's basically the same. We can have d sine of theta. In this case, I'm just deliberately doing this just as a warm-up. Sine 25, and then you should get an answer of, what is this now? 0.55 meters. Okay. So what it means is that it has traveled to the right 1.18 and also upwards of 0.55. All right, is everyone content with this? Ontirense, Miss Charlie, you content with that? Tebogo, Tebo, I think I'm saying it like that. Joseph. Okay, great. Anyone else? Siamonga. Okay, so now the other way to do this is using the actual velocity vector, right? And the way you can do that, you do exactly the same. So you can have find your Vx. This is obviously leading into where you're going to be what you'll be doing today. You can say 0.26 cos of 25, right? So we obviously have to represent a vector as a one-dimensional thing, and that is what we're essentially doing. So we know that it has also traveled 0.356 meters per second, right? And obviously, if we want to find out how much time that was, we just simply use the time. We know that velocity is distance over time, and to find the distance, we simply have to times the velocity with that time. So we know that in the x direction, at the distance in the x direction, which we already got, dx, should call also dx, I hope you know what I mean, is also equal to 0.2356 times that by 5, and we should get exactly the same answer, 1.178 meters. And if we do the same for the, obviously you have to find for the y now, you're just going to say 0.26 sine of 25, and should get, just calculate that for you. So you get a velocity of 1.0988. Just going to exaggerate, it's not exaggerated, but obviously, and we just times, if you times that by 5, you should get the 0.55 as well, meters. All right? So there are two ways to kill this cat. either going with displacement or going with velocity. Obviously, velocity is what we typically use anyway, but this is the start of what we're actually going to be learning, right? So instead of the turtle moving now in one direction, like I said, it can move in a curve path. It can move, up at different types of angles, right? Is everyone content with this? Does everyone understand this? Is everyone happy? Before we move on, it's basically it's nearly the same as, but you'll see, you'll see how we put it up. Okay, thanks, Ebone. Thank you. Okay, just a cute example to get your minds ready for what's to come. Okay, so there's just a bit of talk, and then we can move on. So we talked about this. Yeah, so just give me a moment. And obviously we're just referring to the displacement vector, delta r over there. If you still remember it, and obviously it's changing with respect to time. But what's important here, because it's directed at an angle, it's delta r. We basically have to find the components of the delta r, which is the delta x and the delta t. So in this case, average velocity will be expressed in two ways, which is essentially delta x over delta t and delta y over delta t. Exactly the same as the previous step. Now, yeah, obviously, we have components. And what's important to note is that the magnitude of the average velocity is just the distance between the two endpoints divided by the elapsed time. So, yeah, between the two endpoints, right, and then divided by the obviously time. Then we can let me just that was something. Yes, people keep on asking the same questions. Or it's always available after the. You have all the recordings available. Just ask your colleagues to have yeah, ask your colleagues to show you how to get it. Last one is obviously the instantaneous velocity, and basically it's the limit of the average velocity as the time goes to zero. And what we typically talk along the obviously is the tangent of the graph at a on a particular point. And what they do say here is that the direction of the instantaneous velocity vector is along the line that is a tangent to the object's path in the direction of its motion. Okay, so still kind of the same thing, but all we have is a delta r. It's not typically asked these things, but obviously it's worth mentioning. Is one particular thing to worth mention with this. Okay, then just going on to acceleration. Acceleration, the same thing. We have the change in velocity now with respect to time. So when I'm talking on the change in velocity, we're talking about the change in velocity happening over here due to this delta r, right? And it's again exactly the same definition for them, where your change in velocity will have two components, the delta of Vx and delta Vy. It's a mistake on the slide over there. And then obviously acceleration, it's exactly the same, and it's basically the tangent of the object's path along the direction of its motion. Obviously, you take between 2 points, that kind of thing. But what's important to note here is this. A very special note. Where is this note? What this consequently means, I think it's on the slides, it's under the notes. Let me just quickly share. Oh yeah, it's over here, you can see it. I don't know why I didn't include it in the bloody slides actually. Maybe I should just, is it over here? Okay, yeah, here we go. So just duplicate this and I just add it over here. Okay. This is what's important. Okay. Yeah. This is, I expect you guys to remember this. Very, very, very important. Probably will get some theory in your mid-year test, and this is definitely part of the theory. Is that this should make you now aware based on those things. There are three ways an object can accelerate, in 2 dimensions, obviously. The first one is that the magnitude of the velocity vector, which is speed, may change with time. We obviously know this. Acceleration is velocity over time. We're familiar with this. This is normal. But the other way in 2 dimensions is that the velocity, direction of the velocity vector may change with time, yes, even though the speed is constant. So we can have a constant speed, but it's basically I'm changing direction. And when it does that, that's typically along a curved path. You can imagine obviously a car driving around a bend. In that case, we also have a change in acceleration. And the last one is that both the magnitude and the direction of the velocity vector. So maybe changing theta or changing the velocity might change at the same time. Those are different ways an object can accelerate. So even when we're slowing down, that could be, these are very important to know what is acceleration. So that 3 points, please remember it, write it down. It is super important. Yeah, no one's gonna mind me to post these slides, but anyway, yeah, some of them are not that useful. But yeah, it's in the textbook. It's on page 60. So be fully aware of this. Okay, I hope that's clear to everyone. Yes. Okay. So now I want to get to the fun stuff now, where we actually talk about 2-dimensional motion properly. Okay. Where we can actually solve an example. We're getting there. Just bear with me. Just bear with me. Okay. So let me just quickly unshare. Okay. I'm just continuing with the slides probably. Yeah. Okay. So now we start on 2-dimensional motion. Very important sketch to remember, but let's just talk about it. So in topic 2, we basically studied objects moving in a straight line. And obviously they are under constant acceleration. But in this case, in 2-dimensional, we look at mechanical motion, which is a common motion occurs all over. You can obviously imagine this happening. So what I mean by projectile motion is that we have an object here, a ball, for instance. Essentially, you guys see that before I move on? So I'm going to give examples here. They said anyone who has tossed any kind of object into the air has observed the projectile motion. If the effects of air, resistance, and the rotation of the Earth are neglected, the projected path in the Earth's gravity field is curved in the shape. Page. There's a few things you can actually imagine doing this, but obviously with examples you'll get more exposure on that. Okay. What is important here? So I want you to observe those velocity vectors at each of those points there. So if you look there at the bottom, it's got an X and a Y and an X and a Y. Yes, Mr. Munu. Or Mr. Munu. Keep on forgetting. Hello. Mr. Munu, do you want to raise your hand? Okay, so you keep cutting on my side. I see it's probably network, man. Let me just have a look. Yes, my network is quite poor, it says. Can everyone else hear me? I see one bar on my internet. Am I clear to everyone else? Should I see something? Am I clear to everyone? Oh, my network's good again, right? Can you guys hear me? Mr. Mulu, can you hear me? Yes, fantastic. Okay. Yeah, that's my network. That's my network. Thank you for making me. Okay, perfect. Let me just quickly check again. Yeah, I'm 2 bars. Okay. So what I want you to observe is at different points, look at the velocity vectors, right? Right. So when we're looking at this particular projectile moving in 2 dimensions, what is important to note, right, that your x component is remaining constant all the time. Obviously talking about the velocity thing, right? So that's the first thing on the sketch. It's very important for you to remember. It remains constant all the time, right? However, on the y, look at the y. So the y starts quite high. So longer length eventually decreases and then eventually settles at 0. And then it falls under the gravitational part where it gets accelerated again. So you get a line there and a bigger line there, obviously, until it falls or whatever. But what's important to note here is that the x component always remains the same with respect to time, and the velocity constantly changes. But when it peaks at that point, at that particular part, it is 0. Another way to look at the sketch is this picture, which I'll show you now. Just give me a moment. It's very important. Where is my, why am I going back? Yeah, just duplicate this. I forgot this picture I got. It's exactly the same, but I like the wording on it. Paste it here. Just make it big for you. Yeah. So now it's with rough. It says my network is again bad for some reason. Not sure if you guys can hear me, but again, these are just the components. But as you can see on this side, the y components decrease to gravity. On that side, it increases to gravity when the ball's falling downwards. Obviously, it's accelerating more. And what's important to note is that the x components remains the same. Right? Again, this sketch also, guys, very important to remember, because you probably will be getting in your test some concept questions, multiple choice. We will ask you some definitions and things like that, or some sketches. Obviously, just to see that you understand the theory. All right, and then obviously the top there, your y component 0. That's essentially the most important thing here with this. And then the last one is this, where we look at basically, for instance, if we had maybe a cannonball, right, or a baseball, or some projectile rather fired at a specific speed, let's say 50 meters per second. Obviously, these concepts relate for ammunition, it seems, to predict how far something go. And that R value is essentially called the range, essentially tells the X distance. But what we can do is with these equations you learn in 2 dimensions is predict how far it will actually go. So what they've essentially showing there is that if you have the cannon or projectile faced at 15 degrees, so those are horizontal, 30, 45, 60 to 75, it kind of essentially shows you how far it will actually land. So if you look at 15, not so far, 70, it's quite close over there. 15 and 70 gives the same value. 60 quite far, and then 45, if we angle it 45 degrees, we actually get it the furthest. That's quite interesting. And with these math, you're able to kind of predict, at which angle, for instance, what kind of range do you require? You can actually work out what angle must you have the projectile, through there. But anyway, so that's the kind of stuff we'll be looking at. This is another sketch illustrating something, but what I want to talk to is obviously the equations now. Okay, so looking at our two-dimensional motion, and the motion we'll be analyzing is the projectile, is that what we must be aware of is that our VOX, right, or that velocity which they talk, or how to find the actual the VOX, VOY, is that they'll give you initial velocity, like I mentioned to you before. It's the other one is 50 meters per second, and what you have to do with the velocity to find the individual components is obviously split them into components, the X component and the Y component, and obviously you are aware of how to find it. The X component is with the cos, given that the angles are horizontal, and the Y component is with the sine. So VO cos theta, VOX, X component, VOY. Similar to forces, it's also vector, so we're using vectors. I hope that's clear. But now, this is where the fun part comes in. So let me go to my next slide. So we're obviously aware if something goes at an angle, we've got two components. But now, this is where the nice part is. So I need to look at the left-hand side first. To look at the left-hand side first, there we have our motions in the X direction. Can you guys see that? And on the left-hand side, we have the motions of the Y direction in the vertical or free fall type questions. Can we all see that? Perfect. So now, for the two-dimensional motion, obviously it's exactly the same. However, instead of having just a VO, we have a VOX and a VOY, which is very, very important to remember, right? And obviously the X and the Y is just telling us whether it's initial and final. But for VOX, obviously the initial velocity, which is important, is that VOX is now VO cos theta and VOY is VO sine theta. So that's very, very important to remember, right? So we're basically going to substitute those values in that respective equation. Now, what's important to note is to actually find the object speed. Once we've obviously solved the problem, we end up with Vx or Vy, and obviously theta, and that'll tell us the resultant velocity of the projectile, and obviously the angle with respect to the x-axis of which, I said basically these angles I'm referring to over here, right? The resultant angles. Where was the other picture? Oh, this one? Where's the one? I don't know where the one is. Okay. Yeah, something like that. I think I have a question there. In a second. Oh, no, I don't. Okay. So that's that. Now we're going to build on these equations even further. So it's going to be fun. We're going to see how to talk to each other. So what I'm essentially doing here is basically, okay, so our previous kinematic equations, right, or equations of motions here, is obviously going to be now developed for this particular thing. Now, there's important things to note again, there's no air friction. We always neglect that. And also, the acceleration in the x direction is 0. And the reason why is because air resistance is neglected. So that means AX in your x direction for two-dimensional motion, for our case, always remains constant. So therefore, AX is 0, right? No air resistance. Very important value. So looking at the equation, the VO cos theta, and if you look at the delta x, what we're essentially saying here is we're removing the half 80 squared essentially from each of these things. We will look at where it accelerates in both directions, but for now, AX is deemed to be 0, right? So all what we're essentially left with is this, if you look at the delta x equation, it's basically VOXT, and we're just basically adding what is VOX, and VOX is obviously VO cos theta t. So that's one important equation to obviously remember. So it's all in the textbook, right? However, in the y direction, this is where it gets more fun. So if you revert back here, your y direction obviously has VOY, VOY, and obviously we know that VOY is VO sine theta, the actual the velocity, the sine theta. And in this case, there's gravitation, there's gravity. So we have to keep the G. So AY is essentially G or negative G, as I've said it before. You know, you guys obviously have your own ways of doing that. And we basically substitute VO sine by the initial part. So if you remember your first equation, you know, the first one, velocity, acceleration times time, the VT half AT squared, and the V. So we're basically substituting all the initial velocities with VO sine. Same equation. However, for the X equation, because of no air resistance, and remember that I might ask it, we neglect AX. Is that clear to everyone? Now, what is important to note, the four important notes, that Vx is constant, provided that air resistance is negligible. Very important. This is also on page 63. You have your acceleration is equal to the free fall acceleration minus g. You're obviously aware of that. And the vertical component of the velocity Vy and the displacement in the y direction are identical to those of a free falling body. That's what we assume. And the last part is that the projectile motion can be described as superposition, meaning we basically add them, or we add them separately of two independent motions in the x and y direction. So very important for projectile motion. This is the motion we'll be mostly analyzing, and there's also the relative velocity. So I hope that's clear to everyone. Did everyone get this? So we just remodify these equations. Did we all get this? Any questions around this before I move on? Before we actually solve a problem? Yes, sir. What's the question? You guys all get it? Okay, cool. Now we're just gonna basically plug and play and see if you understand it. So obviously I'll do one example with you, do an exercise, maybe do another exercise, and then we can call it for today and then do another one tomorrow. All right, make sure you practice your stuff. It's not too difficult. It's just that it's just new equations, new knowledge for you to understand now. Okay, so let me crack up on the first one, and then I recommend getting the what is this? Your textbook open and all these formulas. But I mean the formulas are easy to remember. But obviously take it step by step. So this is essentially the first upgrade of knowledge you've probably not learned in matric till now. So well done. I'm hoping to get to at least a few good new knowledges within this thing, but yeah, time is the issue. Can't really cover all the topics. But your topic took us around 4 topics for one semester. Yeah, so maybe 8 topics in total. I don't know. There might be more, but this one is quite small. It depends on the length of the topic. Okay. So let's quickly just get that problem for you, and then we can begin. I think I'm still waiting for the stuff you said you're going to send me. You haven't sent me that questions. College physics. And there's no tutorial session this Thursday. We are partying. It's holiday. Sure you guys are happy about that. Just close certain stuff here.
So,
Yes.
oh, so I'm gonna send the things tomorrow, sir. Because the link right now is not working on this laptop.
Okay, no problems, man. Just send it, you know.
Yes, sir.
I appreciate it.
Yes, sir.
I'm still aware of the YouTube channels you'd like me to send, so I'm gonna send that later on when I'm done the lecture. Just some 2 good YouTube channels for more problems, maybe 2 or 3. Yeah.
So, are your slides also available on the content? Because when I go to content, I don't find your slides. So, the ones that you use on online classes.
I will upload them.
Please do so.
Okay. Cool. Just mute your mic out there. So let me just quickly get copy our first example. So yeah, I'll probably do the one in an exercise you guys can do. Just give me a second. Facebook is not behaving a bit for some reason. So I'm gonna close a few things. Yeah, okay. Just give me a second. Right, here we go. Okay, first example. All right. So typically all the motions or two-dimensional motions will be it'll be a projectile type motion until we come to the relative velocity part where that's a bit different. But I highly recommend cracking these things as soon as possible. Yeah, okay. So looking at this, what we have over here is an Alaskan rescue plane drops a package of emergency rations to stranded hikers. So Afrika and Kiara is hiking, get lost somewhere, and Lucy, Luyanda, Nolo goes on a plane and decides to drop some rations, some food, some Russian beer, Jägermeister, things like that. Okay, but as it's driving past, what you find that the package obviously travels in this particular direction. So what I want to know, they're saying the plane is traveling at horizontally of 40 meters per second. And I want to be fancy, I want to know how much in kilometers per hour that is. Around 144 kilometers per hour seems reasonable. And it's at a height of 100 meters, right? 1.00 times 10 to the power 2 above the ground. See, neglecting air resistance, that assumption will always be there. So the first thing is, where does the package strike the ground relative to the point at which it was released, right? That's the first one. So what they're typically asking there is the X, the range, right? The X. You'll get used to these terminologies. Um, um, the maximum X or the X. And then they're asking what are the horizontal and vertical components of the velocity of the package before it hits the ground, right? So we obviously need to find those ones as well. And then we need to know at what is the angle of impact, which is the last one. Obviously that will talk to, the tan theta thing as before. Okay, so again, A is asking for the range, right? And when you hear range, think of X values. If you remember that in matric, what are those values again? The range and the domain in the range. But I mean, I think the range refers to the Y values in that case, and domain was X. But in this case, range would be the X value. Okay. So first thing is first, we need to know. Obviously, there could be different ways of solving this problem, but we want to know, at that, what's the X thing there first. So what we start off with is, we'll start off with our delta Y equals VO T minus half. Obviously, I like to use half for whatever reason I've explained. Right. Now, I want to know the X distance at that particular point, right? So if I use this as my reference point, and this is back to what we were talking about last time, this is 0. I know that this distance here is negative 100, right? If you recall that. So I know that's negative 1. And the reason why I'm using this is because at this thing, that's where the ground essentially is, right? And then my VO in this case is going to be 0. There is no vertical velocity in this case, right? It's only a velocity in the X direction. Typically these are kind of told in the problems. It says in this problem it says horizontal velocity. It might state a vertical velocity. Yeah, but as you get more mature, you obviously know. So VOY rather must be specific here. Be very specific, is 0. So that kind of falls away. So we all we left with is a minus half the 9,8 meters per second. We obviously we'll include it on the Y, and we have to find the time. So once we find the time, we can essentially just, based on the time, we find the time, it basically reaches that, and it'll also give us essentially the range, right? How far has it basically fell? So I'm talking about the range, I'm talking about this particular distance over here. Okay. So this is the distance of 1. So can you guys find for me time squared? How long did it take to get this? I'm not going to solve this. You guys can easily solve that for me. How long did it take to get to the ground level? You guys can do that. I've talked about this, Joseph. You guys can call it positive or negative. It's entirely up to you. The reason why I keep it negative is because it's going downwards. I mentioned anything to the point downwards it depends how you want to look at it. We've discussed this in class. Negative 100 means it's below the point of projection. Therefore, I call it negative 100, and that just talks to my equations better. I mean, you guys can keep 100, positive 100, positive G. In the end of the day, time will still come out a positive number. I've explained that notation in the last lecture. So just work out my time for me, please. 4.5 seconds. If you're having problems with audio connectivity, probably have to refresh. My network is quite strong now. Yeah, it's probably your network. So you should get around 4.52 seconds. You guys get that? So this is the distance, the time it took rather, for it to land on the ground. All right, but we don't want that. We want to know where does a package strike the ground relative to the point it was released, right? So it gets dropped off there. How far did it travel? Basically in the x direction. Okay, so now we have to revert back to our other formulas now, right? So I'm gonna obviously recap that again. We'll just ignore that. And remember, our formulas in the x direction is delta x equals v oxt, right, plus a half a subscript x t squared. And remember, ax is always 0. There is no air resistance, so nothing else is accelerating the body, right? So this falls away, and our delta x will be equal to Vox times time. So we need to find the velocity of our Voxt, right? And our change in x is quite important to look at this, because your changing x obviously talks to your x minus your initial, but in this case our initial it's 0. There's no initial x distance here, so we don't have to really worry about that. But that tends to come up sometimes. We have to add an extra piece, like another problem with the what is this? You know, the car and the car and the trooper. So our Vox again will be Vx cos theta, if you remember that, and obviously you have to times that by time. Okay. And in this case, the projectile was not fired, or the package was dropped at an angle of 0 degrees, so there was no angle here. So our Vx was 40 cos of 0. If you look at that, that is essentially 1. So just 40. I just put that there because, you know, they kind of skipped that. And with the times by the time given, and that is 4.52 seconds. So we say 40. Can you guys quickly work that out for me to give me that change in x, or the range, or the x? Let's call it x rather. You guys quickly work that out for me. Yes, Afika. That's correct. You should get 180.8. Afika, yes. Okay.
Sir? Sir, is this the only way we can approach the question using the 1 minute pause? Isn't there a way we can answer the question without using time? Can you hear me now, sir? Sir?
Yeah, it's just quite loud on your end, man. Yeah, I'm sure there's another way to approach it. I think you did ask that. That's what I caged. Okay. Maybe we quickly go back. Where am I here now? Okay, so that is A, right? Cool. So then B, what are they looking for? Let's go back. So at B, they want the horizontal and vertical components of the velocity of the package just before it hits the ground. So they're looking for Vx and Vy, right? Not Vox and Vy, I'm talking about Vx and Vy, right? So what I'm going to do, I'm going to quickly go back and just copy the formulas for you so you can see it, and you can find Vx and Vy for me at that particular time. So I'm going to copy it so just so you can apply it at least. So that's at the point of impact. Okay, so they want Vx and Vy, not Vox and Vy. Must be really careful. So I'll place that over here, and you guys can quickly, yeah. So they want Vx, quite easy, and they want Vy. You guys get that? And what's important, what they say, they want it at the point of impact. So you obviously have the time at a particular instant. Cool. So what's my Vx and Vy? I'm waiting on you guys. Fefe, well done. Straightforward, guys. It's not that crazy. You guys get that? Yep, that's correct. Well done. Did everyone get those answers? The load left there for you to do. It's 44.3 or 43? 44.3 meters per second. And for those who've done that, find the angle of impact. Thank you, Tinaye. Find the angle of impact. Okay, I'm assuming you guys can do that. Annual impact is basically stuff you've learned in topic 1. That's why it's so important. You'll be using a lot of that. It's minus 44.3. Keeping that sign is very important. Keep that sign. And we divide it by 40. And you get an answer of around minus 48 degrees. You get the exact answer. You get 47.92. Okay. Obviously, that's like 4 significant figures. You want to go with, yeah, how much is the least here? 2, so we're going to go 48 degrees negative. Do we all get this? We basically at the end of the lecture here. Do we all get this? All right, fantastic, fantastic. Good, good, good. Guys, remember next week, next week, the 4th small class test. We'll cover topic 1, 2, and 3. Small class test, 2%. We'll cover all that you've learned. Small class test, so please be practicing. Just a warm up. Okay, so just me talking to this example. What it basically means is that we've got, we didn't work out the resultant velocity there, but that 48 degrees is here. Obviously not, that's from the horizontal. And if you want to find the exact velocity, you're basically taking that 40 squared plus 44.3. Obviously it's a negative, right? You can exactly find what that package is traveling at and at which angle from there. And you should get an answer of 59.69 meters per second. That's why the angle is negative. Can't be positive because it's not being projected upwards. So all the numbers should make sense. Does the angle have to have a sign? Yes. It's telling you whether it's below the x-axis or above the y. In fact, because it's being fired downwards, it's negative. That's what it should mean. I'm not going to say which date. You should know. Watch the lectures. Yeah. You could say 48 degrees, but you should just know where. You know, the idea is that it's just saying it's around 48 degrees. It's not obviously exactly with that curvature, but that's the idea. Do we all get this? Do we all get this? Any questions, guys, before I move on? Thank you, Ms. Charlie. It's not difficult, guys. It's sometimes easy to understand, but you need to practice, practice, practice to get it in your head. I can assure if I can do it, you definitely can do it. I can assure you. It's just different with the science. Just check that out and engage with me. I'm just looking at something. Okay, so just give you a prescription until I see you tomorrow. I think tomorrow I'll probably see you online, same time. I wasn't sure what's going to come in. Then, but yeah, I'll see you same time tomorrow. But I think tomorrow we might end at 4 o'clock instead. Basically from 2 to 4, maybe it's like a 2 or so hours, just to make sure we cover everything, or as much as we can cover. I was checking something quickly. Okay, I have next week as well, so it's fine. And yeah, so prescription, guys, make sure you do the homework. It's well within your own interest to do it. It's not actually homework, you know, I'm just telling you which problems to do. And we will do one homework tomorrow before I obviously embark on the rest. Make sure you go over it. Let me just, book's not open. Okay. So I'm going to show you do exercise 3.2 at least. This one, it's in your book. I'm going to show you that one. That's a nice one to do. And I might look for another one. And another nice one is, I'm going to give it to you now. Just give me a second. Another nice one. This topic can be a bit daunting for some students, so make sure you practice. Yeah, so, and this one, yeah, it's a nice problems to do. Okay, so do these ones. Number 7, you get the back and do that one. That's just to get you familiar with this kind of stuff. But surely by next week I'll probably finish topic 3. I might spill over to the other week, which I really don't want to do. But we have around from this week 4 weeks left, basically. So there's enough time to cover a decent amount of work. Okay. Yeah, so I think I might just do the, I'll let you know if I'm going to do the morning session. But surely the afternoon one I might just do. But it depends. I need to first just figure out something. Okay, guys. Thank you very much for attending. I hope you learned something new today. I'll post up the slides. And then I'll see you tomorrow. And please just check your announcements on Blackboard. Okay, guys. Bye for now.